Have you ever pondered on the mystery of how we can peer into the inner workings of the human body without a single incision? The key lies in a form of invisible light discovered over a century ago: X-rays. X-rays, a type of electromagnetic radiation, were first discovered by Wilhelm Conrad Röntgen in the year 1895. They possess wavelengths shorter than those of visible light, typically ranging from 0.01 to 10 nanometers. Röntgen's discovery was a groundbreaking one, and it all began with a curious observation that a fluorescent screen in his lab started to glow even when it was placed in the dark. He traced this strange occurrence back to a cathode ray tube, and upon further experimentation, Röntgen unveiled the existence of X-rays. There are two primary ways we produce X-rays. The first is through Bremsstrahlung radiation, or breaking radiation. This happens when high-energy electrons slow down by the electric field of an atomic nucleus, and as they decelerate, they emit energy in the form of X-rays. This is the main method of X-ray production in X-ray tubes. The second method is through characteristic X-rays. When an outer shell electron fills a vacancy in an inner shell of an atom, X-rays are released. These X-rays carry discrete energies characteristic of the material and are useful in X-ray spectroscopy. Now let's move on to X-ray tubes, the most common devices for producing X-rays. They consist of a cathode and an anode enclosed within a vacuum tube. The cathode emits electrons when heated, a process known as thermionic emission. These electrons then accelerate towards the positively charged anode. When the high-speed electrons hit the anode, usually made of tungsten, they produce breaking radiation. But X-ray tubes are not the only way we can generate X-rays. Other methods include synchrotron radiation, where electrons moving in circular paths at relativistic speeds emit X-rays. X-ray fluorescence is another method, where atoms bombarded with high-energy X-rays may emit characteristic X-rays. And then there's gamma-ray decay, where certain radioactive isotopes emit gamma rays with X-ray-like properties. Now that we've covered how X-rays are produced, let's delve into their applications. They have a wide range of uses across various fields. In medicine, X-rays are commonly used for diagnostic imaging, enabling us to visualize the internal structures of the body. In dentistry, they help examine teeth and jawbones. Beyond healthcare, X-rays also aid in material analysis, such as in X-ray diffraction and X-ray fluorescence spectroscopy, which are used to analyze the composition and structure of materials. And let's not forget security, where X-ray scanners are used for baggage inspection at airports and other security checks. In conclusion, X-rays, with their ability to penetrate materials and reveal internal structures, have become an invaluable tool across various fields. From their discovery by Röntgen in the late 19th century to their numerous applications today, X-rays have truly revolutionized the way we see the world.